Yeah, because she's trying to come back and see that's why I went back to work
Okay, so I'm going to start this lecture, and I can't see on the screen here what's up on the screen there. So if I turn around and look at the screen, it's for that reason. I checked with the recap after the last lecture with the screen being half cut off. This was last week. On the recap, because the recap's taken off the computer monitor, it's perfect. So we missed half of the slides in the actual lecture theatre, but if you look at the recap, you'll see everything. So that's at least an advantage. So what I wanted to do today is to finish talking about onshore welding processes, and then go on and talk about offshore activities, which are slightly different. We talked about bugs welding with MIG welding, and then I mentioned that flux cord arc welding was a common technology where you try to minimize the use of the gases that you have to carry around. And you can mechanize that process as well. So this is a mechanized bug that actually feeds a flux cord consumable, and you can see it operating here, and it looks very similar to the bugs for the other processes. And this is the weld immediately after it's been completed, and what you can see with that case is that there's no sufficient detail on that that's any different from a conventional welding process using an external flux for the stick welding or using the gas. This has obviously been cleaned off, because if there's some flux in the system, you will get some slag on the weld that has to be cleaned, but not a great deal. And this is, again, easy to use and is less skilled than the manual welding processes. There are some other types of welding processes that have been coming along more recently, and they've been driven by the fact that we can actually control the power application cycle in the power supply. So with modern solid state power supplies, we don't have a continuous output. We can vary the output in current and voltage, and we can do different things. And surface tension transfer, STT, is enabled by the modern power supplies. And what surface tension transfer is, if you've got a molten weld pool and a wire, the end of the wire periodically dips into the weld pool. The arc is quenched, and then you then get resistance heating of the wire, and then it separates, and you transfer by contact the molten metal from the wire to the weld pool. There's no spray transfer. And the advantage of a surface tension method is that therefore you can weld in different orientations without losing the material. It's been used in certain projects, particularly projects in China very recently, and it's got relatively small pipes and relatively low grades that are commonly used. And then flux cored arc welding is used just to do all the capping layers and things afterwards. So how does this work in practice? Well, this is a sort of schematic of the power supply settings that you will see. Now, some of this is in response to what's actually happening physically. So there's a physical picture of the wire and the electrode surface, and the yellow bits are an arc. But you can see there are different types of mechanisms. They're associated with different features in the current and voltage flow. So you can imagine that we've got a low voltage, and that's the constant arc conditions. And we get that situation like that. And at time t1, you effectively switch off the arc, and the wire is driven forward, and so the wire then comes into contact with the surface. When the wire comes into contact with the surface, current can flow, because it's metal contact. The current goes right up and increases very rapidly, because the resistance goes up as the temperature goes up. And the voltage then goes up slower to match that. So effectively you have something in contact. Now you want to break that contact. So again, you switch off the power that's supplied, and then you switch on a voltage, and at a certain period you get this necking that you can see there, that the heating is focused on that very small area, and effectively you break that contact at this particular point here, and then you get an arc again. But now we have a flat-ended wire and a hump of weld metal that's been deposited. The arc heats that, and the pressure from the arc pushes that metal to the sides, so we can see that there, and we start to form a rounded blob of molten metal on the end of the wire again. And then by the time that's finished and the metal is spread out sideways on the surface, you're back to the original starting position. So the currents come back down to here, which is where we started. So we've got a welding supply that can stop and start the current supply instantaneously. And that's really what you get when you have digital power supplies that are available. You couldn't do that where you had to wind the power up and down with an old-fashioned transductor power supply that was used for welding in the past, for instance. But these modern solid-state systems, you get much more control. And this means you can control the amount that's deposited, because you're putting a little droplet of molten metal every cycle onto the surface and allowing that to spread. And it isn't having to fly through space. So there's no gravity effects, which can be a big problem, particularly in some of the smaller pipes. And here is it actually taking place. This is the route being done by surface tension transfer. You can see the top part of the weld has been done. The bottom part is going here, and this bit is yet to be joined. You get, on this large cross-section, you get a relatively smooth profile. There's no sort of wagon tracks that you can see. No weave is necessary to fill the things in, because we spread out that weld metal. It's a low hydrogen process, and when you control the surface tension forces are holding the weld metal into the gap. So you should get very little penetration, and you don't need a penetration bead, and you don't need a backing strip. Now that's great. Get higher quality weld surfaces. No penetration means pigs can run through the pipe quite nicely. Obviously there's got to be some disadvantages. Nothing ever comes for free. And because we're turning off the current for part of that cycle, we're not melting metal for part of that cycle, this process is slower, intrinsically slower than if you have a continuous running spray transfer process, as you might have in a conventional weld for gas shielded metal arc welding. Okay, so what other processes are there that are used? For some big pipes, we can have a welding process called flash butt welding, where effectively you have two segments of pipe, and you strike an arc between the two sections of pipe, or multiple arcs in fact, and that heats up the pipe, and then you just push it together to actually make the weld. So you have a special clamp for doing this, and these are the important pieces in here. These are insulators, so that you can electrically insulate one pipe from another, and therefore when you can connect them up to the power supplies, you can then have a voltage put across that gap, which will drive the arc formation. It's a much bigger pipe, much bigger clamp. There's a lot of equipment inside the clamp to make sure everything's lined up, and for electrical safety you have to have quite a lot more instrumentation on these systems for doing it. So here's one in service. This is a test, of course, on a test bed, so you can see the arc all the way around the joint. So it's not just one little arc, it's a number of arcs all the way around the joint. And so this is like a one-shot weld. You're not having a welder working round, you're generating the arcs automatically around the whole surface, and then what you do at the end is you press them together to actually make the joint. So the arc is really heating up the end of the pipe. So that's a nice demonstration. That's it happening on site. So you can see the same sort of thing. You see all these arcs here. You can see these ones are slightly more intense there. So if there's contamination and there's bits and pieces on the surface which are different, you can sometimes get non-uniform arcs, non-uniform heating. You have to control the edge preparation quite well because of that. You've got these very big clamps lifting things up, and there are insulators in the clamps to stop the power dumping its way through the supports. You'd kill people if you did that, so you need to have very good safety control. But it's a nice one-shot process. And then the clamp basically contracts and pulls the things together at the end of the process. So you end up with a weld that looks like this. So this is the original line where the metal is there. And you can see the rolled steel microstructure in. You squeeze it together and the material squeezes out sideways and upwards. So you can see that microstructure has been bent around by the plastic deformation that occurs by actually putting them together. But it's a one-shot process. So the weld is made in a single pass, a single station for doing this on the line. And some people think that's quicker. Now obviously you've got this linear defect down the middle here, and if you don't clean the surfaces up very well, you end up with lots of oxides and debris down there. So this requires a higher standard of preparation. But we don't have a V-shaped preparation, we're just squaring off the ends of the pipes in those cases.
The slag levels are less for this process?
There should be no slag, but there will be oxides and debris that come from what was on the surface beforehand. So there's no flux used, there's nothing to produce slag. If you squeeze it enough, hopefully you squeeze out all the low melting point oxide materials, and they end up over here, and this is machined off, as you can see here. And that's what happens in a lot of these butt welding, flash butt welding processes. You squeeze it so much that most of the contamination is squeezed out of the joint. Not usually done on pipes, because then you'd be shortening the length of the pipe and distorting the shape of the pipe. So we rely on very good cleaning and preparation of the surface prior to welding to avoid those oxides that are there. Can be done, can be a good joint. Much less distortion than compared to an arc weld. Tie-ins must be done in a trench. So if you thought it was hard to get at the bottom of a pipe when it's chopped up on supports, imagine doing that standing in the water in the bottom of a trench, working underneath something which has been excavated. It can be done, the same processes pretty much can be used. The clamping arrangements are somewhat different. You can't usually put an internal clamp in, so we have external clamps and systems for holding everything together. So you can see a bend being put in here. There's a welder working on one side with a stick. There's a welder on this side who's also working with a stick. You can't actually see it. And a couple of safety guys standing beside just in case something happens. The clamping is not really done very strongly is fit up by positioning. So you have some underneath supports, you get the bends into the right sort of position, and you line everything up as best you can. Sometimes you can do vertical down, but sometimes you have to do vertical up because the spacing between the parts can't be controlled as well. And that's always a problem with fittings. You can't always support them and clamp them as well as you would like. But you don't usually have productivity limits. You can spend longer lining them up and doing everything by hand. So what's good in these cases is that you have the time and the effort and the expertise to line things up properly. What's not necessarily so good, and you can see an example here, that's the welding sticks sitting in a box. It's open, so if this was wet, they would be absorbing water. So as long as that box had just been opened and it was being used for very quickly, that's probably all right. But if that box had been lying there while you lined everything up, then that probably wouldn't be so good. You'd have more trouble with hydrogen embrittlement. And if that falls on the floor and you weld a stick coated in mud, then that can cause problems. So you need to be a bit careful. Welders generally are quite careful, but they do cut corners if you let them. Okay, what's happened in the recent past in the UK is that the main gas distribution pipes, the very large pipes that move gas around the country, have gone to X80 grade. For various reasons. One, the pipe is thinner because the X80 has higher strength. It can actually, for a given pipe diameter, therefore put slightly higher gas volumes through. It's quicker to weld because the pipe is thinner. At least it would be if you were comparing things directly, but people will always make comparisons with very inappropriate older designs when they do that. It's not actually that much quicker to weld. But we have better welding procedures to cope with it. So the traditional method for welding X80 was just to have cellulosic electrodes used all the way through. And that gave poor toughness and hydrogen embrittlement problems. And so for a long time, X70 was about the limit of what people would weld in service because of the use of these cellulosic electrodes. What we've done recently, though, is done the fast welding that we need for productivity with the cellulosic electrode. So the root pass and the hot pass are done quickly, but then we make sure that we use low hydrogen electrodes for all the fill and capping passes. That gives us the toughness that we need, and there's no cracking in these situations. So actually, there's two different welding electrodes used in this process. So normally, as I said, it would be one electrode for everything, and this time you change halfway through. And that has enabled us to make good use of X80 in the field. There's also mechanised welding that's been developed, again for speed. You get some resistance to weld metal hydrogen cracking because you've got the gases, shielding gases that are dry. And you can use almost exactly the same equipment for X60, X70 and X80 pipes. So you don't have to invest in large numbers of new technologies and train welders up on new technologies. You can use the existing materials. The trouble is, it's really only suitable for pipe-to-pipe joints in good terrain. So if things are going up and down, if you've got lots of bends and things like that, it's not really worthwhile. And for capital costs, buying welding bugs is not as cheap as buying a welding torch. Welding bugs tend to be between 10 and 15 times the price of a simple torch. So you've got to have a long pipeline length. When I say long, I mean 100 kilometres or something like that, just to be able to pay back the capital costs of buying the more expensive equipment. So if you're just doing, 5 or 6 lengths of pipe, a few hundred metres of pipe, that's probably going to be done all by sticks manually. if you're doing a 150 kilometre long pipeline, you're definitely going to be using the mechanised welding technologies. Most fittings have to be welded manually. I would say all fittings, but I did mention under the fittings cold bends in the field, and those can be done in an automatic way if the bending is not too big. Anything which is a tapping point, a port, a T-piece, it's done manually. So these are manual welds, and you might ask, well, why is this all painted white? Well, this has been painted white because it's been dye penetrant inspected. So this is one of the stages of the inspection process to see that those manual welds are good. And this is a couple of welders working together on a small piece. Sometimes if you weld on a fitting on one side, the thermal contraction stresses would pull the part one way. And so if you weld on both sides at the same time, stresses are trying to pull it one way and pull it back the other way, and it keeps it in the centre. So if you balance the welding around the fitting, so people welding at the same rate on the opposite sides, then you often find you get better properties, no distortion, no changes in shape. The other thing that you might want to do is attach connections to the pipe, particularly for cathodic protection. So in those cases, it's a threaded stud that you're applying, which you can then bolt a wire connection on to your CP power supplies and things like that. These are often welded, so the stud goes into a plate, and then the plate is welded around its peripheries with a 2-pass weld. This is like an attachment weld, and sometimes there are problems with lamella tearing in some of the older steel, so you need to be a bit careful about that. But it's a very good way of doing it. If you weld it onto a plate with a large area weld, you don't have the problems of the defects that you will get on a small area around the thread. You can also have pin brazing systems. So there is a system here with a gun. You load a pin and a ceramic ferrule into the system, and the ceramic ferrule can contain a disc of braze, so it's like a solder, like a liquid. The gun will heat up that system, and then there will be some sort of simple electromechanical actuator that just pushes that against the surface and withdraws it, and then allows the braze to flow by capillary attraction into the gap. There's also the necessary cleanliness, so there's a little grinder to grind an area where we put that pin there. So that can be used for making attachments. There are percussion systems which do that just with a big voltage drop. There's a whole range of different portable technologies that enable you to put a small connection, a bolt, onto the surface. And you could choose any one of those really to do things. This is a nice clean picture, so it's never been used in the field. But when they come off the field, they're a lot dirtier than that. So these are pin brazed studs. You can see the grinding around here, where the surface has been cleaned back to bare metal. You can see the stud, and you can see the metal has been dragged into the gap between the two underneath the stud by capillary attraction. So that's the process. And you can do that on a big square attachment, and you can see the full bolted joint in this particular case. Very good, very high quality, good conductivity, which is what you need. But you can check that because you can measure the conductivity between the stud and the surface very easily. Finally, you need to actually document what you're doing. So this is a welding procedure specification which you have to have for each welding process that you use within the pipeline manufacturer. So a welding procedure specification has quite a lot of information on it. It has job information to start off with. It has material information, qualified ranges, you can see there. Underpinning this welding procedure specification, you have what's called a process qualification report, which contains all the test data to prove that this process works. So this has been qualified for thickness ranges between 4.76 and 32 millimetres. So they've done tests across that range. So you make sure that you're within that range. You get the processes, pseudo metal arc welding, the position, fixed horizontal. Yep. You have the pass sequence in a little diagram here. You have the root preparation and the edge preparation. Do we need post-weld heat treatment? Well, there's a pre-heat treatment. The pipe is heated to 100 degrees C, and the flange is heated to 150 degrees C for this joint in a fitting case. So everything is written down. And then there are settings for the power supplies. Pass number 1, one welder, welding rod that's 3.2 millimetre diameter. It's negative polarity, it's a cellulosic. The current has to be between 63 and 88 amps, and the volts 25 to 40. Welding speed 1.92 millimetres per second. It's all written down. Heat input calculated. You can actually measure that as things are going. So there's a range there. And what you're doing as a welding engineer is trying to keep the welders to this preparation. So the guys that were standing beside, who may well have been the engineers, not only are there for safety, they're also to make sure that the welders are not suddenly welding too quickly or doing something like that. They check the settings on the power supply. Modern power supplies that are digital, you can say, this is welding procedure number 11. See this one here? So you have actually a button on the power supply which says procedure number 11, and it automatically goes to the settings that you require for that. So you have absolutely got to control every step of the welding process to ensure that you produce a reliable process in the field. Now this is done before you even start the project. Your job though, if you're a welding engineer, is to make sure that on the project it's actually kept to that standard. And that's much more easy nowadays in the days of digital power supplies, because you can hardwire that into to the process. In the past, welders would say, I can do almost anything, and it's my skill as a welder which determines whether or not we get a good joint. Nowadays, we have to work to a certain standard for doing that.
Excuse me, sir.
Yeah.
What's the difference between 5G and 6G position?
Horizontal, 6G pipes incline.
What's that?
5G pipes horizontal, so you're welding everything from overhead,
Yeah.
vertical, and down onto the weld.
Yep.
6G, same welds, but the pipes inclined at an angle
Yeah.
rather than horizontal.
Yeah. So it's how you set the pipe up, basically. So how do you qualify welders? You weld lots and lots of pipe pups. So this is production quality pipe, which has been cut up into sections, and your trainee welders weld them together, and you test them and you cut them up and you keep welding them until you believe they meet the standards. So you can have productivity tests, you can have quality tests, and you can have performance tests, all done on material that you've specified, using processes you've specified, using welders you're training to try and actually make things. And it's a lot of work. And you don't let people actually start to weld the pipe unless they've been trained. So you cut test pieces out of the material. So these are strap test pieces here, square bar, rectangular bar test pieces, round bar test pieces, Sharpie test pieces, you name it, you cut any test piece you like out of the weld and make sure that the weld metal meets the standards that you've set down for each welder who you're training. I can't emphasize the point about training the welders enough, because if you let welders be free, they won't follow the procedure, period. There's a famous case in the Tyne. Welders get paid by the hour, and they don't like working on Friday afternoons. On the shipbuilding, they used to weld the root pass in a hull plate in a ship, and then it was getting a bit late and they didn't want to spend all the time putting in the fill and capping passes, so they put some welding rods into the gap and just welded the capping pass over the top. So the welding engineer comes along and he sees a perfect weld with a good root pass, you can see from one side, and a good capping pass, good quality, workmanship standards very high, signs off the weld. But if he'd been sensible, he'd have thought, how could the welders possibly have done that weld in 2 hours, when if I calculate all the weld lengths and things like that, it's a 5-hour job? So he should have been suspicious. So when the ship is launched, as it happened once, and it breaks its back at the end of the slipway, because this is the defect that's cut the strength of the ship down sufficiently, who loses their job? Who loses their reputation? The welder that did it, or the welding engineer that signed it off? It's the engineer, yes. So your job as an engineer is to make sure the welders do what they're told. And good luck to you. That's what I can say. So processes. In summary, we've got manual cellulosic welding as being the most common field process, particularly if the terrain is difficult. We've got mechanised processes where suitable, large diameter long pipes generally. And 30 kilometres has been put down there. I've seen people use mechanised equipment that they've already bought and that they've re-qualified for shorter runs. But if you're buying it afresh, that's the 30 kilometres. There's a shortage of skilled welders, particularly those who are skilled enough to do root passes. And they command a premium. And therefore, if you can find ways to de-skill the process, and you've got enough money to invest in capital, then techniques like flash butt welding, semi-automatic processes, those sorts of things become more palatable for you to do. It's the reason that China had the STT process on a couple of their projects was because they didn't have enough skilled welders available at the start of the process, and we needed to be, the companies involved in that needed to be up and running quickly. So they looked for processes that involved less local skill. Eventually, I think now there's enough trained welders in China to be able to do the projects that are currently running, but at the time that those results were generated, that wasn't the case. And trained welders trained to Chinese standards and trained welders trained to UK standards are not the same. I'm not saying which is right or which is wrong. They are just different. Steel specifications in China and in the UK are different because the main sources of iron ore have different levels of contamination in. Chinese steels have a lot of boron in, which is almost absent from UK and European steels, which have a lot of phosphorus in. So they are just different. You need different procedures. And you need to recognise that if you're then going to be in a multinational company, that you can't just pick and choose process from one country and apply it in another one. It doesn't necessarily work. High strength pipeline steels, we have to make bigger use of low hydrogen electrodes, because otherwise the difference between the yield stress and the ultimate tensile stress is so small, you've got very little in hand if you overload the system, and fracture properties from hydrogen embrittlement are a serious problem. Mechanised welding, though, is certainly capable. Okay, so that's onshore. I'd like to move now offshore. So what's the difference between onshore and offshore? Well, you've got to get it right offshore, because when you've actually finished all your welding and pipeline construction, you're putting the pipe under maybe a kilometre and a half of water, and it's quite difficult to go in and repair things that you've got wrong. Also, you don't spread your pipes out like you do onshore. You have to have a barge, a lay barge, on which those pipes operate. So basically the welding position is fixed, It's just that it moves as the ship moves through the system. And you have all sorts of welds. You can have tie-ins and T-pieces. You can have mechanised welds. You can have manual welds. You've got differences between risers and landfall areas. You've got different areas in the pipeline. But we want to get it as well as possible right the first time. If we have to repair things, we will sometimes weld underwater, but we don't weld underwater in the water. We weld underwater in a chamber where the pressure is higher than atmospheric pressure because of the head of water above you. And we call that hyperbaric welding. So hyperbaric welding is not welding underwater, it's welding in a high pressure, which just happens to be underwater in these particular cases. And the pressure has a big effect on manual welding. And the length of time that a welder can operate to high quality is very short under these hyperbaric conditions. So we try to make more use of automated processes where possible under those circumstances. So we don't want to have to do things with divers and welders if we can avoid it.
With the hyperbaric welding, would you get more diffusion of hydrogen and other gases into the liquid weld?
Certainly increasing the pressure, you might expect increasing the solubility of hydrogen. Actually, the pressure effect on solubility is relatively small. So people say that, yeah, hydrogen processes are worse, but actually solubility isn't too different. So what the problem normally is that under a hyperbaric welding condition, there's nowhere for the hydrogen to escape to. So the ambient hydrogen levels go up, and that has a bigger effect rather than the pressure that you're dealing with.
Potentially explosive environment.
Absolutely, yeah. So we're going to talk a bit about lay barges because that's where the welding takes place. S-lay, J-lay and reel barges. And we'll talk a bit about offshore pipeline welding, and basically the processes are the same. We've got manual shielded metal arc welding, we've got mechanised gas metal arc welding, mechanised gas tungsten arc welding. So we've got manual metal arc, MIG and TIG welding, as I've talked about before, just the same as on land. There's a bit more use of radial friction welding and other one-shot processes because productivity on the barge, an area of operation on the barge might be limited in some cases, particularly for smaller lines. So there's two types of lay barge. There's what we call S-lay and J-lay. An S-lay, this one here, the pipe comes out of the back of the barge, and it's sometimes called a stinger. It's a bit like the sting of a bee. But it goes down, and then it goes horizontal on the bottom of the sea, and it has the shape of an S. So the welding is horizontal, and the pipe ends up horizontal. That's mostly used where the water depth is not very big. If we go to deeper water, we use a J-lay approach, and in J-lay the welding is vertical, and we go down, and then it goes horizontal at the bottom, shape of a J. So S-lay and J-lay just really is the shape of the pipe during the process. And J-lay is deep water and S-lay is shallow water, and there's some overlap between the two. So sometimes if you're in that middle range, sort of 800 or 900 metres deep, you might go for whatever barge is available for the cheapest amount of money, rather than worry too much about whether it's the most appropriate technology. So here is the S-lay technique. You've got these tensioners. You've got this pipe you're welding. You mustn't let go of it and drop it on the seabed. So you have these tensioners just to hold it, and then you join bits of pipe on the front. When you're happy with it, you move it back a little bit. It goes off the back of the barge. Barge can go forward a little bit, and you're gradually moving forward, and the pipeline is disappearing off the back of the barge. But everything you do has to be done on the barge itself.
So, is the cooling, how is it cooled? When you finish welding, is it cooled in the stinger or?
Just in air. There's no forced cooling in these cases because that can make martensite formation more likely. So you don't control the cooling, you allow it to cool in air.
before you take it to the stream?
Oh, yeah, there's lots of things because it has to be cooled, inspected, repaired,
Before you release
coated before you release it. And so everything happens. It's not just the welding, it's everything happening on that barge. So the barge is like a factory moving along, doing these things.
How you are then hydro testing it in the factory?
It isn't.
Operations.
It's operation. Because remember that you've got a very big hydrostatic head around the outside. So actually they're much less likely to leak than a land. Because if you put it down, you've got a 1 kilometre head of water. That pressure is much higher than the pressure of the gas that you're putting along the pipeline. So, and if it leaks in, you get a water analysis at the end of your pipe. So, they aren't generally hydro tested. So this is the stinger on the back. You can see the pipe going in. It's being guided and shaped, but it's just coming off the back of the barge. And it's moving relatively slowly. We're not talking about going at meters per second here. We're talking about a few things. You might get 3 pipes jointed, completely done, 30 meters. The barge will move forward 30 meters, and then it will anchor again, and then the process will go on. It might be a slow movement forward, because it depends on the sea conditions. So here's an S-lay barge. So here's the pipes disappearing out the back, and you can see this is a twin pipeline system, 2 pipes. Helicopter landing pad on the top. Ship delivering pipe segments on the side. Stacks and stacks of pipes. And then along the middle, there is all the welding and inspection and coating stations. And then people are living around the outside. There's no accommodation module on this block. There'll be a separate thing for doing that. Notice the sea, quite flat, quite nice. Most of these things are done in the summer when the sea conditions are relatively flat. Because you don't want this thing going up and down like this way in front of the lake. So here's a typical system. So you'll have fit-up welding at the top, and then a welding stage, then a capping and welding stage. You might have a double jointing station where you join 2 pipes together, and then those are included. So there's another 3 welding stages there. So by that time, hopefully you've got your root pass, your hot pass, all your fill passes and your capping pass done, and it's cooled. And then you've got radiography. In this particular case, you might have automated ultrasonic as well, inspection of each weld. At that point, you decide, do I have to repair? And if you repair, you clamp and you stop and you repair at that particular point. And when you're happy that the repair is okay, so you radiograph, ultrasonic again, then you let it go back. Got corrosion wrapping, and if you've had to repair maybe mastic application on the actual weld, mastic cooling, by the time it gets to the stinger at the back here, you hope that everything has been done. And if you've got your process set up correctly, you've inspected, you've checked everything, it should be right all the way through the system. The pipe that comes out the back is a proper pipeline with no defects in it, and it's okay for use. So all of those stations have to work at the same time. So unlike in a field weld, in a onshore, where you can have processes operating at different speeds, each team here has to operate at exactly the same speed to make the productivity. So your repair welders have to work just as fast as the mainline welders. So there's several stations for welding, inspection and coating. Each station is on the critical path, therefore you minimise the time at each station. So there's a lot of use of double jointing, a lot of use of mechanised welding, a lot of use of automatic ultrasonic inspection, and you use analysis techniques like the fitness for purpose specifications, which we'll talk about later, to decide whether, if you do find a defect, whether we have to repair or not. So you make a decision. The decision is not defect, therefore repair. The decision is defect, how critical is this defect? Do I need to repair, yes or no? And that is a slightly different way of working to work onshore, where we tend to repair everything. Typical pull time on the lay barge That's about 9 minutes. So that's for each section of pipe. So it's possible to lay about 2 kilometres of pipe in 24 hours. And if you double joint it, you can double that. So 3 to 4 kilometres a day is quite a good productivity rate. But if you've got, 200 kilometres to do, that's 50 days of work, solid. You have to be able to maintain that over a long period, and you can't maintain the weather for that length of time in most places. So there is a small amount of manual shielded metal arc welding, just as you can see here. This is a cheap picture. This is just the same as the onshore. So this is an onshore weld, but the same process. I just don't have a picture of people using cellulose sticks on a lay barge. There's a large amount of mechanised welding. Again, this is the same picture because I don't have a picture on the lay barge. I've never actually walked along on a lay barge while it's been in operation. They don't like people from outside coming in, generally. And twin head bugs for increased productivity they use. You've seen these pictures before, again, just for completeness. So these are systems. So this is a system that I have seen, which is what they sell to the people that operate lay barges. So this type of McDermott system with the various supports around the outside that clamp onto the parts that allow you to hold and weld the pipe segments. You can see them in a factory, and then they disappear off to the barge, and they're never seen again by the rest of us. So it's a combination of clamps, holders, and welding machinery, supplied by the welding power supply manufacturers generally, because everything has to integrate together. Now, just like on onshore, we use mechanised welds, and the main failure is lack of sidewall fusion. So again, you've seen this picture before. It's the onshore example. We have them on offshore as well. I haven't got a good example offshore, but it's the same there. So we have mechanised gas shielded metal arc welding. We have repetitive defects such as lack of fusion, which you want to avoid, because lay barge time is very, very expensive. I did hear somebody tell me that the lay barge that they were using was £2 million a month. Now I don't know how much that included, whether that was everything. Yeah, but it's a lot of money, so you want to make the best use of it. So we use automated ultrasonic inspection instead of radiography, because we want to size defects so that we can make a decision using fitness for purpose standards about whether we actually repair. And sometimes when you qualify the welds, you measure weld toughness using crack tip opening displacement methods, which are not usually specified for onshore, to really make sure that this is going to be an okay welding process. So we basically do extra work offshore because we can't afford to get it wrong. And we apply engineering critical assessment to decide whether we're going to allow the defects that we've got to exist or whether we actually have to repair them. Because what we're trying to do is reduce the number of repairs that we've got to do, because the more repairs, the slower the process, the more it costs. But you want to make it so it works, because the last thing you want to do is put a badly repaired pipe down and find that it leaks and there's seawater coming out at the end of your pipeline, not gas. We make some use of corrosion-resistant alloys. Some duplex stainless steel is used, some martensitic stainless steel, often bolted. Some high nickel alloys. These are expensive. They're slower to weld because we need to control the heat input in those processes. We can get very good quality though, so that's okay. And we use the gas shielded processes, the TIG and MIG welding, with an internal gas purge in the pipe to protect the root paths from oxidation for those. So these can all be done offshore, and the welding processes, procedures can be set up for all these materials. When you go away from plain carbon steels or carbon manganese steels, the welding is more expensive and more time consuming. So people try to minimise the use of these corrosion resistant alloys in the pipes where possible. So you might have a riser which has corrosion resistant alloy to some handling platform, and then you might do something on that handling platform, and then the main pipeline to land is just a carbon steel process. It just depends on what the analysis for the field actually is. So here is a purge clamp. This is a clamp used exactly the same way as things before. So you've got your clamping faces here, and you've got these things here which actually put gas into the region around the welds to prevent the oxidation. And this is where the gas comes from. So the clamp offshore is not the same as the clamp onshore because of this requirement for extra protection. And again, that can be pulled through, and you've got an umbilical there, you can top up the gas and do things with it that way around. So it's a slightly more complicated clamp. You'd really like to have a totally automated process, and for some of the smaller pipes, and particularly some of the tie-ins that you do, and some of the sidelines and things like that, and things on rigs, you tend to use thinner pipe sections, maybe only 12-inch diameter, and there are processes now that can completely weld those automatically. So this is a duplex stainless steel pipe segment being welded together by orbital TIG welding or gas tungsten arc welding. Very high quality welds, very clean. As long as everything's set up, you just push a button and the machine does it all for you. Great for small things, not good for big things. And there are quite a lot of processes where small is what you've got, so that's okay. So that's where I'm going to stop for today. Next lecture next week, I will talk a bit more about the offshore welds, and I'm going to then focus on weld inspection and repair techniques right at the end. But inspection and defect analysis is quite critical, particularly for these offshore systems. So I'd like you to get an impression of the sort of defects and what they might look like in the inspection technologies. I recognise that modern systems have better ways of identifying some of the defects, but I wanted to show you, at least for radiography, what some of these things actually look like, because that's where we started, and that will be next week.
My suggestion is about X80 stress corrosion, X80 welding. But I'm trying to figure out some things. I don't know when welding X80, which welding process is overmatched.
We always overmatch.
X80.
Yeah. You always overmatch because you want the failure to be in the line pipe, not in the weld. The X80 consumables are not necessarily X80, they're more like X95 or something like that, or X100 even, yeah, that's right.
There are different consumables for different pipes.
Well, what is claimed to be an X80 consumable will overmatch X80, so it will have a higher X rating if you measure just the properties of the consumable.
Just looking at the progress on the laying, on the welding,
Yeah.
vis-a-vis the laying.
Yeah.
If it's a trenched pipe,
Yeah.
we can see that the progress is usually very small. So when does the trenching take place?
Well,
Does it take place at a certain section?
you do